Galvanometer. Today's topic is galvanometer. Galvanometer is a device used for detection and measurement of small electric currents. Being a sensitive instrument, galvanometer cannot be used for the measurement of heavy currents. So we use galvanometer to detect only a small amount of currents. Working principle. It works on the principle that a current carrying loop placed in a magnetic field experiences a torque. We know that a current carrying loop has its own magnetic field around it. When we place this current carrying loop in another magnetic field, so both magnetic fields interact with each other. So due to this, a force is applied on the current carrying loop and a torque is generated. Construction. Most modern galvanometers are moving coil type and are called as D'Arsonval galvanometer. Parts of galvanometer. A U-shaped permanent magnet with concave pole. Here you can see a U-shaped permanent magnet with concave poles. These poles are concave shaped poles. Flat rectangular coil of thin enameled insulated wire C. On this rectangular coil, wire is wrapped around aluminum frame and is suspended by conducting ribbons. A pointer or needle. Another important point of galvanometer is pointer or needle. A soft iron cylinder B. Here a soft iron cylinder is used to intensify the magnetic field of permanent magnet. A scale. Rectangular coil A, B, C, D of fine wire wrapped around an aluminum frame is suspended by conducting ribbons. This rectangular coil A, B, C, D is wrapped with wire around an aluminum frame and it is suspended with the help of conducting ribbons. A soft iron core F is fixed between cylindrically concave poles N and S of a permanent magnet. We place here a soft iron core represented by F between the concave poles of permanent magnet, between the north and south poles of the permanent magnet to intensify the magnetic field of this permanent magnet, because the field of permanent magnet will be radially due to this iron core. The suspension wire T1 is used as one current lead to the coil and the other terminal of the coil is connected to a loosely wound spiral T2, which serves as a second current lead represented by T2 here. A cylinder of soft iron is placed at the center of coil, which intensifies the magnetic field. This iron core is used to intensify the magnetic field of permanent magnet because this iron core has high permeability and makes it radial by concentrating the magnetic field lines due to its high permeability. because the permeability of this iron core is high, so it will intensify the magnetic field of this permanent magnet by concentrating it radially. So you can see here that magnetic field of this permanent magnet is radial due to this iron core placed between this permanent magnet, between these poles of the permanent magnet, north and south poles of the permanent magnet, and this is here placed to intensify the magnetic field. Working. When a current I flows through the coil, a magnetic field B is set up which interacts with that of permanent magnet, producing a torque. Tau is equals to BINA cos alpha. As we know that current carrying coil will have its own magnetic field, and when we place this current carrying coil in a magnetic field of permanent magnet, so magnetic field of current carrying coil and the magnetic field of permanent magnet interacts with each other, and due to this interaction torque is produced, and that torque is equals to tau is equals to BINA cos alpha. Here B is magnetic induction of the radial magnetic field, and N is number of turns in the coil, A is area per turn of the coil, alpha is the angle between the plane of the coil and the direction of magnetic field induction B. I is the current flowing through the coil. Since magnetic field is radial and the plane of the coil is parallel to the magnetic field B, so torque is equals to BINA, because cos alpha is equals to cos 0 and cos 0 is equals to 1. 1 multiplied by this term gives us tau is equals to BINA. The torque rotates the coil and twists the suspension until it is fully resisted by the suspension. As a result, a restoring torque comes into play, trying to restore the coil back to the original position. As we know that when torque is produced in a coil, so coil starts rotating, and due to rotation of coil, the suspension wire is twisted, and suspension wire tries to restore the coil back to the original position by applying restoring torque on the coil. If theta be the twist produced in this strip and C be the restoring torque per unit twist, then restoring torque is equals to C theta. When the coil is in equilibrium, then the deflecting torque is equal to the restoring torque. Deflecting torque is BINA, that is equals to restoring torque, that is C theta. And from here we can rearrange the equation to get current I is equals to C theta divided by NAB, where C divided by NAB is a constant. Therefore, angular displacement theta produced being proportional to the magnitude of current, I is directly proportional to theta. A sensitive galvanometer is one which produces large deflection for a small value of current. We can make the theta large by keeping this term C divided by NAB small. So when C divided by NAB is small, we will get a larger deflection for small amount of current. We can read this result on to the scale. A light beam is reflected from a mirror M carried on the suspension ribbon onto the scale, and from a scale we can read the result. In sensitive galvanometer we can have the large angle, and it is done by the help of the small mirror attached with the coil along with lamp scale arrangement. In this lamp scale arrangement, the beam of light is directed from the lamp towards the mirror, and then this beam of light is reflected from the mirror and it produces a spot on the translucent scale placed at a distance of 1 meter from the galvanometer. As we know that this coil is rotating coil, and due to rotation of this coil, this mirror also rotates, and the spot of light moves along the scale after the reflection from the mirror. The displacement of the spot of light on the scale is proportional to the angle of deflection. Another method of finding the angle of deflection of the coil is pivoted coil galvanometer. In less sensitive galvanometer, we can fix or pivot this coil by the help of two jeweled bearings, and by the help of these two hair springs we can generate the torque, the restoring torque. So restoring torque in this type of galvanometer is produced by the help of these two hair springs that are also used as current lead T1 and T2. Here a light pointer is used, that is aluminum pointer, and it moves over the scale, and by the help of its movement we can get the angle of deflection of the coil theta. So this pointer is attached with the coil. Coil is rotating coil, and due to rotation of coil this pointer also moves along the scale, and the movement of the pointer along the scale gives us the angle of deflection theta.